this lesson, we are going to learn about a type of spectroscopy called photoelectron spectroscopy, also known as PES. If you remember, the first spectroscopy that you learned about was called mass spectroscopy. That led us to learn a little bit about isotopes and how you can measure the percent abundance of different isotopes of an element, or find out information about the structure of a molecule, because you can see what kinds of mass particles come off when the material goes through the mass spectrometer. Well, in this case, the photoelectron spectroscopy is going to let us learn about the electrons of an atom in the electron cloud. So, couple ideas. What goes on is we bombard an atom or a molecule with a certain wavelength of electromagnetic radiation. So we know what the energy is going into the atom. If an electron absorbs enough energy, it will eject itself from the electron cloud and use the extra energy as kinetic energy. It's motion as it leaves the electron cloud. So really what we're trying to do is measure the ionization energy, the amount of energy it takes to actually remove that electron. So that's the idea behind this process. So we can determine the binding energy, which we learned as the ionization energy of the ejected electron, by using this equation. The binding energy is the energy of the photon that we shot at the atom minus the kinetic energy that the electron possesses as it leaves the electron cloud. So the values of binding energy are going to tell you a little bit about the elements that are present, the orbitals from which those electrons were ejected. Couple ideas you can see here. Lower binding energies are going to be seen for valence electrons because they are held less tightly. They are further away from the nucleus than the core electrons are. So you've got a much stronger pull on core electrons than you do on valence electrons. So the energies that are lowest actually belong to the valence electrons. And then for molecules, there are correlation tables that you can use to identify the composition of the molecules based upon the energies that are being given off by the electrons. So here's some visuals, which is really much more helpful than me talking about what we're talking. So you've got different wavelengths of light shining on a piece of metal. When metals are involved, Einstein coined this photoelectric effect because we can get electrons to come off the surface because of this idea. So we shine different wavelengths of light on the surface of a metal. And in this case, there's not enough energy to cause any electrons to get emitted. So the electrons have more binding energy, have more ionization energy than what this red wave shows. The green wave and the blue wave have enough energy to cause the electron to absorb energy, leave the electron cloud, so it excites the electron, and it leaves the electron cloud traveling at different velocities. Notice that, so the red is lowest energy, the blue is highest energy. Notice that the velocity of the electrons are different. The binding energies are going to be the same, however. So if you were to do this energy minus this energy, you would get the same value as doing this energy minus that energy, if we're looking at the same electron. So again, you've got valence electrons and core electrons. Core electrons are going to be held much more tightly. So if the core electrons are held more tightly, it's going to take a larger amount of energy to cause those electrons to break off. So here we're applying an X-ray in order to get a core electron to leave. And so again, the binding energy is going to be the difference between the wavelength of light that you shot at the atom and the energy that the electron has as it's leaving, the kinetic energy that the electron has as it's leaving. If you were to just use UV light, which is less energy, maybe now we are hitting a core electron or a valence electron instead of a core electron. And so less energy involved here means the electrons with this binding energy are now the ones that are able to come off. So the binding energy, again, is the ionization energy that we learned in first year. The ionization energy is going to be equal to the wavelength of light, or the energy of light that we shine on the surface of the material, minus the kinetic energy. And we can get the kinetic energy by measuring the velocity that the electron is moving as it leaves the nucleus, the electron cloud. Here's some units that you might see attached to these types of questions. EV is an electron volt. So notice that electron volts have a joule per mole relationship. And then if you need more, we're going to do some other activities on the photoelectron spectroscopy or photoelectric effect. But here's a couple websites that let you kind of do some simulations. And that's it. There you have the idea.